everyone, good morning. I am Diksha Kaushal, your chemistry master teacher, and welcome to Vedantu NEET English. So, how are you everyone? Am I audible? Am I visible? Everybody in the chat box, if I am audible and visible. Hi everyone, good morning. I am Diksha Kaushal, your chemistry master teacher, and welcome to Vedantu NEET English. Okay. So, camera only told me that yes, I am audible and I am visible to you guys. Okay, so I think now there is no echoing, anything is there. Okay, so yes, everyone in the chat box, so let us start the session. Today we are going to do solutions chapter. So how many of you find solution chapters easy or difficult? Because for me it is actually a very chill pill, very easy kind of chapter, right? And easily we can complete this chapter today itself within 2 to 3 hours. Very simple chapter it is, and we are going to complete this along with the previous year questions, right? So how many of you find this easy? How many of you find this chapter difficult? Yes, thank you, thank you, thank you. Looking like a wow. Okay, so firstly let us see the comments of students. So Roshni, Saif, Pradeep, thank you, thank you, thank you. You guys have also done your homework. Then there is Jaya, Sneha, Gamin, right? So very good students who do their homework. And Tanuja, Philo, Varshit, Disha, right? All of you, right? Vishnu, Priya, all of you, I want all of you to do your homework that I gave you, right? Because I am eagerly waiting for your homeworks in the comment section, right? So, okay, now let us start the session without wasting any time, right? Okay, yes, solution is very difficult for me. Don't worry, from today onwards, it will become very simple for you, right? We'll make it very, very simple for you, okay? Yes. Is it sufficient for JEE? If you're talking about JEE means, yes, you can crack JEE means. But JEE advanced students always, NEET is like NEET, there is seats are less, right? Right, the competition is that thing. To get into that 50,000 government seat, that is the main thing. But in JEE advanced, the level of question is definitely different. Like the level of JEE advanced question are definitely high. But the concepts will be same, right? If you want to clear up your concepts, you can watch this lecture. But yes, you need to practice, right? Okay? Yes? Okay. So now let us start this session and this chapter, starting with the concept of homogeneous and heterogeneous. A very basic thing firstly we are going to talk about. Firstly, what is homogeneous? What is heterogeneous mixture? Homogeneous means which has only one phase. Heterogeneous means which has more than one phase. Basically, in homogeneous, for example, you have, if I talk about a solution, for example, you have a beaker, in that you are adding sugar, in that you are adding salt, right? You pick up 1 spoon of that sugary water or salty water, it will be little bit salty or sugary what you have taken. The second will also be same, the third will also be same. Basically, what we want to say that all the particles of sugar are distributed in that beaker equally, right? There is uniform distribution, that is a homogeneous mixture, right? Like air, salt water, sugar water, alloys, these are your alloys like brass, these are your homogeneous mixture. What is a heterogeneous mixture? Here we say it is its composition and properties. For example, you have water, in that you are adding soil. Now soil will settle down, right? It will not get uniformly distributed throughout the water. That is why that is called, its composition and properties different throughout the mixture, right? Soil, it will definitely settle down here, right? Soil will be present here, and here you have a lot of water, right? So that means it is not uniformly distributed, right? So that is called your heterogeneous mixture, right? As you can see the examples here. Here you are adding sugar to the water, that is a homogeneous mixture. Here we are adding water, we are adding salt or not salt, we are adding sand or soil to the water, that is our, it can settle down here, it is settled down here, and rest of it is your water, right? So that is your heterogeneous mixture. Next is solutions of. Now firstly, we are going to talk about heterogeneous mixtures here. Solutions are homogeneous mixture of two or more than two components, right? So if you talk about any solution, there are two components present, that is solute and solvent. Solute is always in less quantity. Solute is always in less quantity. For example, you are adding sugar to a beaker of water, right? You are adding little bit, 1 to 2 to 3 teaspoon of sugar, right? That is because that is in the less quantity. That is why it is called a solute. Which is in more quantity, that is your solvent, right? It is in more quantity. And one more thing, in our chapter, I will represent solute by 2 and I will represent solvent by 1. Right, I have already written the representation here because when we are going to do the numericals, basically the numericals they are going to ask from colligative properties, right? Theory part I will tell you what they can ask you regarding solubility, Henry's law, they will ask you the theory part, but from want of factor, from colligative properties, they will ask you the numericals, right? For the numericals, to make it easy for you, right, you should have this thing in your head that solute is denoted by 2. Right, I am telling you, like most of the books it is represented by 2, in some books it is represented by A, in some books it is represented by B. So have that fixed thing in your head that solute is your 2 and solvent is your 1, right? And then together they will form a solution, right? Okay, now let us see next thing, that is your type of solutions. This is there in your NCERT as well, right? But not the questions are not asked from this particular chart, but still you should go through it once, right? So for example, they are saying there are 3 type of solution: gaseous, liquid and solid. If you talk about gaseous solution, gaseous solution means the name on which the solution is, that is basically your solvent, right? Gaseous solution means your solvent is always going to be gas. Here solvent is always gas. So we are variating the solute here. If solute is also gas, if solute is liquid, if solute is solid. Gas into gas, like our air, right? That is mixture of oxygen and nitrogen gases. For example, we are mixing 2 gases, right? One is solute in less quantity, other is in high quantity. That is your gaseous solution with gas as the solute. If you want to talk about liquid and gas, now liquid is the solute, it is in the less quantity, right? So here it is chloroform mixed with the nitrogen gas, right? Don't say carbonated drinks, right? In carbonated drinks like soda, right, Limca, Coca-Cola, Pepsi, in all these drinks you have carbon dioxide, that is the gaseous is less, but the liquid is more. Here we are saying the gas is more, the liquid is less. So the example is chloroform mixed with the nitrogen gas, that is a liquid mixed with the gas. Next is solid in gas. So when you can add solid in gas, here they are saying camphor in nitrogen gas. For example, camphor is the solid, yeah, that is the solid, right? So camphor, we are adding the nitrogen gas, little bit of nitrogen gas we are adding into that, right? Next is liquid solution. So your solvent is going to be liquid, solute will vary. For example, you have gas as the solute in the liquid, that is gas as the solute in the liquid, that is nothing but your carbonated drinks also you can talk about, right? Here they have given the example of oxygen dissolved in water, like in ocean, right? What exactly is there? How can aquatic life survive? Tell me one thing, can you survive without oxygen? Because we have air, like in this we have oxygen, we can breathe, right? So similarly, aquatic animals also need that oxygen. But ma'am, they are not living in land. How they are getting that oxygen? Because oxygen is, plants will give out oxygen, right? And animals will catch that oxygen. But that oxygen will stay in that water for some times. Only then plants, animals can catch that oxygen and inhale that, right? So there is oxygen dissolved in your ocean, right? Okay, so that is automatic, that is nature. Right, so here they have given oxygen dissolved in water. I have given you a realistic example for that, right? Then you have liquid in liquid, so very simple. Anything you add milk in water, that we like, that is our milkman is very famous for that, right? So ethanol dissolved in water. This so beta you are not that much. You are not officially applicable for this thing, right? Ethanol in the water, right? So this is solid and liquid. Okay, solid and liquid. If I talk about liquid, you're adding solid, right? That means solute is your solid. So anything, salt in water, sugar in water, anything what you are adding, right? Salt, sugar, they are solids, right? Or your water, that is a liquid, right? So glucose dissolved in water, anything, right? Now, next is you have solvent, that is your solid, right? And gas is the solute. Now, example is solution of hydrogen in palladium, right? So, palladium. Now, for example, this is your one metal, right? Now, you are adding gas. Gas is your H2, right? Basically, this is used in your catalytic hydrogenation, right? In catalytic hydrogenation, we always say that you have hydrogen you are adding and then you are using some catalyst. So basically, what kind of mixture is that? That is a mixture of gas and solid, right? Then you have liquid in solid. Liquid in solid. You have, for example, amalgam of mercury with sodium. Now, sodium is your solid. Amalgam of mercury. Mercury exists as at room temperature. Mercury is a liquid. This we have been studying when we were a little kid. You remember we were studying this. Yes, ma'am, we used to cram this thing. Yes, ma'am, mercury is liquid at room temperature. The same things, right? So liquid, mercury is liquid and this is your solid, right? Next is solid in solid. So solid in solid, you mix alloys you can talk about, right? Copper dissolved in gold, right? Any alloy if you talk about, right? That is basically solid in solid solution, right? So that is a basic concept of homogeneous, so that you can deep dive into it. You can realistically feel that how this is actually applicable in our daily life, right? I would say this chapter you can actually relate more, because you know chemical kinetics you won't be able to relate in your daily life, though it is applicable in your daily life, but you don't observe that on daily basis. But solution chapters, you observe those things in daily basis. You will get to know so many answers of your questions, right? That is based on the laws of solutions, right? So you're going to have fun today, right? Don't worry about that. It's an interesting chapter, right? So now here you have, on the basis of amount of solute, you have three kind of solutions, right? So it is basically based on the solubility, right? So what is solubility? Solubility is the amount of solute that is dissolved in a beaker. For example, I have a beaker, I have this much water. I don't know if 5 spoon I can dissolve it in, if 10 spoon I can dissolve in it, I don't know, right? So the amount of solute, if I can dissolve 5 spoon of sugar in it, so 5 spoon of sugar is the solubility of this beaker. If I can dissolve 10 spoon of sugar, right? After that, it will be like, I don't want to dissolve more of sugar into me, right? So that means it is like, I don't want to dissolve enough of solubility I have already done. So even you can study to one extent. If I am teaching you for 3-4 hours, you can study still. You'll be like, yes, ma'am, I can study. But if I teach you for 10 hours, you will feel a little bit, okay, ma'am, only in exam time I can do that. But otherwise, daily basis, ma'am, I'm not able to do that, right? Ma'am, I need self-study also. Right? So there is a point of saturation for you. So in the point of saturation, we are going to define these three solutions. First is your unsaturated solution. It's like, okay, ma'am is teaching for 3 hours, I am fine, I'll be able to listen to ma'am, whatever ma'am is teaching, right? You're totally fine with that, right? So that is a solution in which more amount of solute can be dissolved at a given temperature. For example, you have a beaker, you're adding 1 spoon of sugar, right? Have you done this in your house? You will teach concentration as well. I will teach concentration that is applied here, right? That is applied in your solution chapter. I will teach you molarity, molality, everything I'll teach you. Weight by weight, weight by volume, volume by volume, all of those things. But in detail, I have covered that in some basic concepts of chemistry. A detailed lecture I have taken on concentration, right? Okay. So, here students listen. For example, I am teaching you that you have 3 hours, hai na? 3 hours, 4 hours, you're like, okay, fine. So basically what is happening, your mom has given you a beaker, right, a jar of water. She is like, some guests are coming to home, I want to make some lemon water for them. So do one thing, you just mix this sugar into this water. Has this ever happened to you? For me, so this was my main task in kitchen. That was my main task, to stir the sugar in the beaker. Okay, I used to stir it for hours and hours, and I used to mix a lot of sugar into that, right? So that is what my task was. So I hope so you also have done this, right? This is what we kids are for. Like for mothers, we are the helping hand, right? So yes, so unsaturated solution. This is that solution only. When you're stirring, you're like, okay, the sugar is being dissolved here. That means the solution is yet like, okay, I am able to dissolve more of sugar. You can add more sugar into me, right? That means if I can teach you more, you are in the situation of unsaturated solution, right? But if you're like, ma'am, enough for today, ma'am, I won't be able to study more. Ma'am, please give me break. Some of you ask for break in between, ma'am, please, ma'am, give me 5-minute break. What is that? That means you have reached your saturation point. You are like, ma'am, I'm not able to use my brain more. Ma'am, my brain is not braining anymore. Right? So you have reached your saturation point. That is, no more sugar, no more solute can be dissolved at a specific temperature. Right? At a specific temperature, cannot be dissolved any further amount of solute. Right? And this is a saturation point has achieved. Saturated solution. Super saturated solution is when you are like, have you seen those gulab jamun, right? That gulab jamun, have you seen that gulab jamun? In that, the sugary solution that they make in gulab jamun, in rasgulla, right? Oh my God, sweet dish. Oh my God, festive season incoming. No, so festive season is going, so that's why I'm talking about sweets and all, right? So here, super saturated solution is what? For example, in that sugary solution, what you have, it's not like they have dissolved the sugar at a normal temperature. No. What they do, these sweet shops, what they actually do, they heat up that beaker, they heat up that jar, they raise the temperature so that the solubility can be increased, right? So here, a solution in which amount of solute is more than it can dissolve at a particular temperature, right? You raise the temperature, then you make it dissolve, then you cool it down, right? So that is your super saturated, because it was not able to dissolve that much solute, but still you are forcing it to dissolve that much amount of sugar, right? Wait a minute. Okay. Now, next is concentration terms. So, I'll tell you a brief about concentration terms. Okay, guys? So, I'll tell you a brief about concentration terms, right? So, now let us see. Basically, there are what kind of concentration terms are useful to you. Guys, are you able to see the full image, right? The full board is visible, no? Okay? Yes. So, concentration terms, let us talk about. Very simple it is. Very, very simple. So, whenever they have given you weight by weight percentage, weight by volume, well, you don't have to remember any formula here. I am telling you, don't remember any formula. Just remember, whenever this is given, just remember solute by solution. Solute by solution. Because here they have given you percentage. That means it will be multiplied by 100. Whenever you are calculating any percentage, in that case, it will be always multiplied by 100. So now if they have given you weight by weight, you will see weight of solute by weight of solution multiplied by 100. They have given you weight by volume, weight of solute divided by volume of solution multiplied by 100. If they have given you volume by volume, you will say volume of solute divided by volume of solution multiplied by 100, right? If they have given you this in the form of ppm weight by weight. In case of ppm, you just need to multiply this by, everything will remain same. Just multiply this by 10 raised to power 6. Because million is what? 10 raised to power 6. So here they are saying parts per million. In million, how much amount of solute you have? In percentage, you multiply this by 100. In parts per million, you multiply this by 10 raised to power 6. Rest of the things are same. That is solute by solution. Weight by weight, weight by volume, volume by volume. According to that, your this weight and volume will change. That's it. Very simple. You don't have to mug up everything here, right? Okay. So now next is your concentration terms, where we are talking about mole fraction. Okay, so now mole fraction is a very interesting thing here, right? And this you will use in your solution chapters a lot. Like in every step you will use mole fraction. At every step you will use, right? So without ppm means parts per million. Okay, that means parts per million. As you can see here, ppm means parts per million. That, for example, for million of kids, there is one teacher. Then I am that one teacher for million of students, right? So that is parts per million, right? For example, something is in a very less quantity, so we will not talk about it. A sugar is not in parts per million. If something is in a very less quantity, like in our air, the carbon dioxide is in very less quantity, right? So that is your ppm, parts per million. In million, how much amount of that solute you have, right? So now let us talk about the mole fraction. So see, students, mole fraction is also very simple. Just remember one thing, mole fraction basically, it is to calculate the, right? We will talk about different kinds of mole fraction. First, you just remember the simple definition. For example, you are calculating the mole fraction of A. It is represented by this. You will see this looks like a X, but actually it is, we pronounce it as chi. Okay, chi, right? So it is pronounced as chi, although it looks like an X, right? So whenever I'll say chi A, that means I am talking about mole fraction of A, right? Chi A. That means mole fraction of A. So for example, you have 100 components. Let's talk about, for example, you have 10 components, right? You have 10 components, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You want to calculate the mole fraction of 8th component. So that will be number of moles of 8th component divided by mole fraction of all the components, all the 10 components, right? So always it will be the, for any, in a mixture, you are calculating for one particular component, right? So it will be number of mole fraction of that component divided by total number of moles of all the components present in that mixture, right? And here always remember, when you calculate the mole fraction of all the components, this chi1 plus chi2 plus chi3, so on up to all the components, right? If it has 10 components, that will be equals to unity. If it has 2 components, that will be equals to unity. If it has 1000 components, it will be equals to unity. So mole fraction of sum of all the components is going to be equal to unity here, right? Mole fraction of all the components is going to be equal to unity here, right? Okay, so this concept is also very useful to you, right? You will apply all these things in solution chapter. Next is most important concentration term is your molarity and your molality, right? So molarity and molality, let us talk about molarity and molality. So in molarity, if you talk about riti, I taught you this with the help of Varun. Who is Varun? Varun Dhawan. Acha, how many of you are a fan of Virat or Varun? What should I write? Virat and Varun both will work here. What do you want me to write? Let me see. Are you a cricket fan or a Bollywood fan? I am not even a fan of Virat. I am not even a fan of Varun. I am a fan of chemistry. That is why I have added it here. Right? Virat. Chal. Yes. That is our proud of our country. So let us write Virat. Okay. So this is your Virat. Now, Virat, from Virat we will be able to understand molarity. Now, the main problem that students face, they get confused that, ma'am, students, MSD, yes, I know, but MSD, we will not be able to understand this with the help of MSD, right? That is why Virat. Okay, if my term would have been something else, I could have used anything else also, right? Anything else I could have used. It depends on what I want you to learn, right? So it doesn't matter to me whether I'm a fan of MSD or Virat. What matters to me is what is the thing that I want you to learn, right? So here you have Virat. Now the main problem that student faces, ma'am, there is just one difference. It is your molarity. This is R and this is your molality. This is N. Molarity, R-I-T-Y, and there's molality. So when you have R, you will say volume. R and this is your V, right? R and this is your V, right? So volume R. That means in molarity you will have volume. That is only difference in these two definitions. So molarity is what? Molarity is number of moles of solute divided by volume of solution in liters. And what is molality? That is number of moles of solute divided by weight of solvent in kilograms. So the difference is, here you have volume, here you have solution, here you have mass, here you have solvent, and both of them are in the SI units. Here it is in liters, here it is in kilograms. Now this is a very, very important concept, right? Very, very important concept, right? Now always remember, the things that are dependent on the volume are also dependent on the temperature. The things that are not dependent on the volume are not dependent on the temperature. Here molarity is directly, it is dependent on volume because it is inversely proportional to volume. So it is dependent. Molarity is temperature dependent quantity. But your molality is not a temperature dependent quantity because it is not dependent on the volume. Okay, tell me one thing. Out of these three, can I say this is also temperature dependent? This will also be temperature dependent because both are dependent on the volume, and this is not a temperature dependent quantity, right? This is not a temperature dependent quantity, right? So it's not only about molality and molarity, rest of the quantities also you can tell, but the most famous is molality and molarity, right? Okay, now I'm going to erase this here. Yes. So now there are some relations here. For example, you talk about the relation. For example, they have given you density, they have given you molar mass, they have given you mass of solute, they have given you molarity. You have to calculate molality. Usually you will not apply this thing, but yes, in detail we have covered this in some basic concepts of chemistry. We have also done numerical on these bases, right? Okay, but in solution chapter they will not give you this. Like high probability they will not ask you to calculate molality this way, but you never know, so you should know the formula, right? Then there is this thing, if they have given you mole fractions, right? They have given you mole fraction of A, mole fraction of B, you know the molar mass of A, then you have to calculate the molality, right? Here what you will do, you will apply this formula and you will get your molality, right? Okay, you will get your molality. Why molality is so important? Because molality is used in two main colligative properties, that is elevation in boiling point and depression in freezing point. That is why I am telling you that molality you will use in your throughout the chapter, right? They will not directly give you this is the molality. They will ask you to calculate the molality. Very rarely they will give you the mole fraction and then calculate molality. This is also very rare chance that they give you density, molar mass and molarity, then you calculate the molality, right? But high chances, very high chances that they can ask you, they can give you some percentage and they can ask you the molality. For example, they have given you 10% of ethanol, 10% of ethanol in water. Now, they have not given you any molality here. You have to decode it yourself. So, why I have taught you W by W percentage, why I have taught you W by V percentage, V by V percentage, why so? So that you are able to understand the concept of molality as well. Now, for example, this is given to you in the question that this is weight by weight, right? So, always remember, what is weight by weight? That is weight of solute divided by weight of solution, multiplied by 100, right? So if I assume, if 10% is given, 10 gram is solute. I am saying, so what is solute? Ethanol in water. That means ethanol is the solute here, right? 10 gram of ethanol in water. Water is the solvent here, right? Now, in division, you have weight of solution, right? So, if I take this as 10 and I multiply it by 100 to get 10%, This should be 100. Only then I can get 10% of weight by weight. That is why here you will always assume that is in your denominator, you will always assume this as weight of solution as 100, right? So here I will assume it as let weight of solution be 100 grams, right? If I am taking this in grams, I will take this also in grams, right? Unit should be same. Now, what I will do, I know this is my weight of solution. So, weight of solvent is going to be, what is a solution? That is solute plus solvent. So, solute plus solvent is equals to your solution, is equals to your solution. So, can I say solvent will be solution minus solute? What is solution? That is 100. Solute is what? 10. So, it will be your 90 grams, right? It will be your 90 grams, isn't it? It will be 90 grams. Yes, 10 gram of solute, 90 gram, 100 gram solution. Very good. So, now everything is given to you. Can you calculate the molality here? What is molality? That is number of moles of solute. Everybody in the chat box, solute is 2, right? So, number of moles of solute divided by weight of solvent. Solvent, I told you, I will represent it by 1. I will not, every time I will not write solute, solvent, solute, solvent. Just keep this in your head that, okay, number of moles of solute means 2 and this is weight of solvent means 1. If I am talking about weight of solvent in grams, I will multiply this by 1000. If it is in kilograms, because in the definition it is in kilograms, right? It is in kilograms, but I want to write it in the grams. So, I will multiply this by 1000, right? So, it will be number of moles, that is your W2 by M2 multiplied by W1 into 1000. Now, you have W2 also. This is your W2, weight of solute. This is weight of solvent. This is your W1. And what is mass? What is molar mass? That is your M1, the molar mass of this ethanol. No, not ethanol. This is not ethanol. The molar mass of water, because this is molar mass of, no, solute only, yes. So, this is your M2, right? Okay, so you have W2, you have M2, you have W1 and easily you can calculate the molality. So, this question they ask you, right? They will give you something like this. First, you have to decode it and calculate the molality. Then you will apply this molality concept in your colligative property and you will calculate the colligative property there, right? Okay. Okay. Okay, students. Yes. Dikshi, Vishnu, Sukanya, Sneha, Tanuja, Markovnikov. Oh, Mini Crafter. Yes, students. Yes. Okay. So, tell me the answer for this one. 2017 question it is. Let us see how many of you can answer this. Yes. So, let us see how many of you can answer this. Which of the following is dependent on temperature? Which of the following is dependent on temperature? We know that molarity is dependent on the temperature because it is dependent on the volume, right? Rest of molarity is not dependent. Weight percentage, W by W percentage, it does not depend on the volume. Molality also does not have any volume. Mole fraction also does not have any volume. So, molarity is dependent on the volume, right? Yes, A is the correct answer. Next is asked in 2015-2011. What is the mole fraction of solute in a 1 molar aqueous solution? Right? They have asked you the mole fraction, right? They have given you the molality, right? And from that you can calculate it, right? Mole fraction you have to calculate. Molality they have given you. So, you just apply the definition of molality here. What is the definition? If it is given, your molality is equals to 1. So, can you say 1 mole of solute is dissolved in 1 kilogram of solvent? Because if your molality is 1, that number of moles of solute should be 1, right? Your number of, your mass of solvent should be 1 kilogram only, then molality is 1, right? So I'm assuming this as 1, right? So 1 kilogram means 1000 grams, right? So now, can I say I have, this is my water, right? Because in aqueous solution, that means my water is the solvent. Water is the solvent. So if water is the solvent, that means 18 gram per mole is going to be the M1, right? Here this is your W1, weight of solvent. 1 mole already N2 is given to you. So what will be N1, number of moles of solvent? That is your given mass, that is 1000 divided by 18. This has been asked 2 times, 2011 and 15, right? So 1000 by 18. Now what I can do, I just apply the formula of mole fraction. Mole fraction of the solute. That means this. So it will be N2 by N1 plus N2. What is N2? That is 1 divided by 1 plus 1000 by 18, right? Just calculate this, you will get your answer. Okay? Yes, I think, let us see the answer. Yes, it is 0.0177. You just need to do the calculation here. 1 by 1 plus 1000 by 18. 1 by 56.7 is 56.5, and this will become C as the correct answer, right? Okay, just have to do the calculations here. Is that clear to everybody? Student, was that clear to everybody here? Right? Okay. Shall we proceed with the next thing, that is your solubility? Right? Shall we start with the next thing, that is your solubility? Right? Okay. Got it? Very good. Now, let us talk about the solubility case here. So, in solubility, very simple it is, right? As I was telling you about the amount of solute that is dissolved. Solubility is the substance at its maximum amount of solute that can be dissolved in a specified amount of solvent at a specified temperature, right? So, solubility depends on so many things. It depends on the nature of solute. It depends on the nature of solvent, right? Whether the solute is easily able to dissolve. For example, your concentration also, your concentration in study also depends on the subject that you are studying, right? So this is the subject that you are studying. This is you. It also depends on you. It also depends on the subject here that you are studying. It also depends on the teacher who is teaching you. So let it be, this is the teacher and this is the subject. If subject is interesting, teacher is also interesting, then you can easily be like, okay, I can understand this concept, right? So here, this is your temperature and pressure. Mainly, so we are going to talk about temperature and pressure in these cases, and the questions are asked from temperature and pressure only, right? So we'll talk about different kind of solubilities. First is your solubility of solids and liquids. So solubility of solids and liquid is very simple, right? Just assume one thing here, that you have a beaker in which you are adding sugar, right? So what will happen here? So first thing is, solubility of solid in liquids varies greatly. This though you don't have to understand. First is dissolution and there is crystallization. So very beautiful concept here. Okay, very beautiful concept, right? Mentioned in your NCERT. So I'm going to write it here. Very simple thing. It's like equilibrium. So I'm representing the sugar molecules with these white dots, right? That are already dissolved. These white sugar molecules are being easily dissolved, right? Now, at one point, this solution will be like, I don't want to study. So now tell me what happens when you are studying. When you are studying, what happens exactly? You're like, ma'am, I'm really tired, ma'am. I don't want to study, ma'am. Please, ma'am, give me break, ma'am. I don't want to study. I'm still like, no, you have to study. Now, at one point, what will start happening? It's not like I will teach you, you won't be able to understand that. You will be able to understand that what ma'am is teaching. But at one point, you will start forgetting the past things that you have read. This happened to you, this ever happened to you, right? So, for example, you have reached your threshold. You are like, ma'am, I am not able to understand more, but still I am teaching you. So, at one point, what will be there? you won't be able to, for example, in exams, what happened? In exam, what we do, we are like 15 hours, 20 hours, we are just reading, we are, trying to absorb everything. So what happens at one point when you are reading, after 10 hours, 50 hours, your brain will stop working. But you will be like, oh my God, I have my exam tomorrow, I have to study. So what will happen? You will start forgetting the things that you have studied earlier, right? So same thing is going to happen with this, our solution, right? So it is able to dissolve so many sugar particles. It's like, okay, my rate of dissolution is very good. But then I started to add more of solute, right? I am starting to add more of solute. Now this solute in our eye, we will think that this solute is not dissolved. But in reality, this solute, I'll change this, okay? I'll change this solutes. Everybody see this very carefully, okay? We will think that this solute that I have drawn with blue pen, are you able to see this blue pen, right? This solute then I am drawn with this blue pen, or should I increase the pen size, right? This solute that I have drawn with blue pen, you will think that, ma'am, I am not able to dissolve more of knowledge, right? But exactly what is happening, but when I will teach you, if my method is good, you will be able to understand everything. It's not like, so these blue dots will start getting dissolved, right? These are getting dissolved, but you're forgetting the older part that you have studied. That means these white dots are getting converted to the blue ones, right? These white dots are getting converted to the blue ones. Understood what exactly I am saying? Basically, I am saying there are two concepts at equilibrium, when in reality you are like, mom has said that, okay, dissolve this sugar. Like, mom, no more solute can be dissolved. But in reality, what you can see in that in this beaker, ma'am, there is no more sugar that I can dissolve. I am saying sugar is getting dissolved. Ma'am, how? Because the rate of, what you can write here, the rate of, write it down, very beautiful thing, rate of equilibrium here, okay, rate of dissolution. So when you dissolve the thing, that is equal to the rate of crystallization, right? It is equal to the rate of crystallization. Crystallization means when it is getting from sugar, dissolved sugar to undissolved sugar, it is getting. When these white dots were getting back to the blue dots, that is the rate of crystallization. Here I can write, when white dot is getting back to the blue dot, that is your rate of crystallization. When it is getting dissolved, that is your white dot, right? So when it is getting dissolved, right, and when it is getting converted from dissolved to undissolved form, the rate has become same. In our visualization, we will see, ma'am, nothing is happening, it is not getting dissolved. In reality, it has established the equilibrium between rate of dissolution, the rate in which sugar is getting dissolved, and the rate in which old sugar, dissolved sugar, is getting back to the sugar crystal form, right? Okay? True, ma'am, happens everything, like me, continuous asking break. Yeah, Sukanya, that's why I took that example. I know your saturation point. Ma'am, please, ma'am, give me break. But student, today I'll give you very less break, okay? So now, because I have class in DNA batch at 2 p.m, so I need also to take that class. I need to have lunch also, right? So that's why I will not give you break that much. We'll see, right? We'll see. Now, factors affecting the solubility. There are basically very important factors. First is the nature of solute and solvent. Every solid does not dissociate into liquid, dissolve into liquid. That is true. While sodium chloride and sugar dissolve readily, naphthalene and anthracene do not. These are just examples that naphthalene and anthracene, they will not be dissolved in water. A solute dissolves in a solvent if, very important thing, like dissolves like. That means polar will get dissolved in polar, non-polar will get dissolved in non-polar. Non-polar will get dissolved in non-polar, right? For example, water is a polar solvent. So HCl can be dissolved in that, right? Because HCl is also polar. If something is non-polar, like benzene is non-polar, so it will be dissolved in a non-polar solvent like CS2, carbon disulfide, right? Okay. Please teach NCERT line by line series organic. Yes, I'm going to teach that. Don't worry, I'm going to take up your alcohol, phenols and ethers. I have taken up haloalkenes, halorines, right? So I'll be taking alcohol, phenols and ethers this Friday. Okay, don't worry about that. Right? Okay, understood. Now, next is your effect of temperature. So always remember, it depends whether it is an exothermic reaction or an endothermic reaction. So the solubility of sodium solid in this significantly affected by temperature changes, right? Because this is an endothermic reaction. Remember, whenever you are adding solid or you are adding sugar to water, right, the energy is required. You have to stir it, right? The energy will be required so that sugar get dissolved in it, right? So that is an endothermic reaction. So in an endothermic reaction, when you increase the temperature, solubility increases. But for an exothermic reaction, when you increase the temperature, solubility decreases. That is the main point here, right? That is the main point. If it is an exothermic reaction, the solubility should decrease. This is from equilibrium only, right? This concept is basically from equilibrium only, okay, right? We are just writing it here, right? If we have endothermic, temperature increases, solubility increases in case of solids and liquids. If you have exothermic, temperature increases, solubility will decrease. It is inverse relation is there, right? Next is your effect of pressure. There is no effect of pressure, right? There is no any significant effect of pressure. Why? The reason is because solid is also incompressible, liquid is also incompressible, right? So when you are applying pressure, there is no effect on your solubility of solids in liquids, right? Next is solubility of gas in liquids. If you have solubility of gas in liquids, you are adding gas. This is the best example is, think about the Coke, right? Think about the Coke, Coca-Cola bottle that you love, right? That you just try to like, okay, I'm not feeling good. My stomach is like so much stomach ache I'm feeling. Please give me some Coca-Cola, right? I have eaten too much. Please give me some Coca-Cola. Just you excuses that you make to drink Coca-Cola. It's been 2 to 3 years. I don't know how, what is the taste of Coca-Cola? What is the taste of these Pepsi carbonated drinks? No idea on that. Yes, I drink Fanta sometimes, right? Because that's love for me. Limca sometimes, maybe once a year or so. But Coca-Cola, I don't even remember the taste of it, right? So when you study too much, right, of these things, then you know that what you are drinking. Sometimes it's okay, but some people have the habit of drinking it on a daily basis, like water. After every meal or whenever they are going out, they just, because it is addictive, right? So when you taste it, even I will start feeling addictive, right? So you have to cut down to that. So it's a very good time, right? You are a teenager, you should cut down to these things. That's my advice to you. Rest is totally your choice, right? So yes, gases dissolved in liquid. Now, when you talk about gases, so this is form of homogeneous solution. Solubility of gas, liquid depends upon nature of solute, solvent, temperature and pressure. Let us talk about the solubility of different gases in same solvent varies considerably, right? We will talk about this in Henry's law, right? For example, gases like N2H2 dissolve in water only in small extent, whereas NH3, HCl are highly soluble in water, right? So according to gases also, we will have different amount of solubility that they will have. Like solids also had different amount of solubilities. Gases also have different amount of solubilities, right? Next is your temperature. So here you have direct relation. Okay, tell me one thing. Will you ever drink any Coke which is hot? For example, will you ever drink a hot bottle of a Coke? What you ask anywhere, you're a guest, someone is asking you that how much amount of, do you want chilled Coke or what? You will say, yes, I want chilled Coke, right? To the shopkeeper also you ask for chilled Coke, right? You wouldn't ask for a Coke that is outside there. Why? Because what is the chemistry behind that? That these chilled Coke, when it is at low temperature, solubility is high. Solubility is high. That means that gas, that carbonated drink is more dissolved. That carbon dioxide is more dissolved at low temperature. That is why you like to have it at low temperature. You have that fizz, right? So what exactly happens when it is not at low temperature? The carbon dioxide is not in the very good solubility form. The carbon dioxide, as soon as you open the bottle, the carbon dioxide will escape. That is why you will feel like you are drinking just a sugary water which has sugar. That's it. The fizz is basically of that carbon dioxide that produces that kind of thing that you love, right? So basically that means here you can see that solubility, if your temperature increases, solubility decreases, right? This is for gases in liquids, right? Right. Next is your pressure, right? So now pressure, basically here we will talk about Henry's law, right? So Henry's law stated that when your pressure increases, your solubility will also increase. That means they are directly proportional to each other, and on this basis we have a proper thing, that is your Henry's law, right? Here they have less pressure, right? Because only one weight is there. Here you have 3 weight. That means more pressure you have. So what you can observe here, that here the molecules are away from each other, and here the molecules are very close to each other. So more the pressure, the molecules get close to each other. That is why the solubility increases on pressure, on applying the pressure, right? So solubility increase with increase of the pressure. Now let us see the Henry's law here. What exactly Henry's law state? Very, very important law. So in this law, firstly that this law stated that solubility is directly proportional to pressure, right? That was given by Henry's law, that at a constant temperature, mole fraction of gas. Now we will talk about when this mole fraction came into our knowledge, right? So basically Henry stated that solubility is directly proportional to pressure. When you increase the pressure, solubility will increase. But then Dalton modified this thing. He said that take mole fraction, take solubility in form of mole fraction. And he said that pressure is basically directly proportional to the mole fraction, which basically means we are talking about solubility only. So here from this he stated that pressure is equals to KH mole fraction, where KH is your Henry's constant. And this is a very, 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 very important formula, important thing, right? Okay, is not in our syllabus. Henry's law not in syllabus. No, that is in the syllabus. That is in the syllabus. Yeah. Don't miss this. Don't miss this. When you are reading solution chapters, you should never miss these things, right? Okay. Next is at constant pressure. At constant pressure, right? When your pressure is constant, your KH is inversely proportional to your mole fraction, right? Or you can say KH is inversely proportional to your solubility. So what in the question they can give you different values of KH. They can ask you write the solubility order of these, right? So for example, they have given you 5, they have given you 10. This is the value of KH. This is for A, this is for B. The solubility of A will be high as compared to B, right? So they can, in the question, they will give you different values of KH. They will ask you the solubility order, right? Okay. Yes. Now, next is, let us draw the graph. So what was the equation? The equation is P is equals to KH into mole fraction. So can I say Y is equals to mx plus C, where your intercept is equals to 0, slope is equals to KH, and x is equals to mole fraction, that is chi. Y is equals to pressure. So Y is your pressure, right? Partial pressure of the gas, right? This is your mole fraction, that is x-axis you have mole fraction. And here intercept is 0, that means it will start from the original. And your slope is, that is m is equals to kh. So here you can write slope is equals to kh, right? Slope is equals to kh. That will become your graph. They can also ask you what is the correct graph of Henry's law, right? Okay. Now let us see the This is basically the unit. The unit of kH can be torr or bar, right? Because mole fraction is unitless, right? So you have P is equals to kH into mole fraction. This is unitless. This is unitless. So that is why the units of kH is same as pressure only, right? So different gas have different value of kH, as I have already told you. kH value of gas increases with increase in temperature. As you increase the temperature, kH value will increase, right? kH value will increase. Higher the value of kH of the gas, lower will be the solubility. As I have told you, kH is inversely proportional to the solubility, right? Okay. Next is different values at same temperature, function of nature of gas. This already told you. Higher the value of kH at given pressure, lower the solubility of the gas. This also we have already talked about. Now, next is the concept of vapor pressure. Okay. Next is the concept of vapor pressure. Yes, students? Any problem till now? Any problem till now? We are moving towards the concept of vapor pressure. Yes, students? Any problem? Any problem? Any problem? Any problem? Achha, have we done the limitation? Have we done the applications? Let me see if you have that here. Okay. So I'm writing here only. I'm writing some applications of Henry's law. First application of Henry's law is your scuba divers. Scuba divers. Right? I'm writing the direct application that you will see in your daily life, right? Because they can ask you this, right? That why this happens. So when you talk about scuba divers, right? So what exactly happens in scuba diving? When you go lower, right, in the ocean, under the water, what happens? Your pressure increases. Why? Because you are also, it's not only the atmospheric pressure, it's also the pressure of water that is acting on you. So the pressure is increasing. We know that if pressure increases, solubility will increase. And in water, we human beings, we need what? We need oxygen. So the solubility of oxygen in our blood is increasing. So if the solubility of oxygen in our blood is increasing, that means we are happy that our blood has more oxygen. But the problem is when you will come out, but while coming out, what will happen? But while coming out, this is exactly mentioned in your NCERT, but while coming out, because pressure decreases, solubility will decrease. Now that oxygen that was there in your veins, in your blood, in your hemoglobin, now that oxygen, like now my solubility has decreased. Now I want to go out. For example, earlier you are a very good friend with someone, now you are not a good friend with them. Now you want to, get out of their life. So similarly, oxygen is like, I am not soluble now, I want to go get out of your life. Yeah? Oxygen wants to get out of our hemoglobin, out of our system. That is the reason there is one condition, that is bends, right? That can cause a lot of things like the burst of your your veins, right? So many things can happen. It can even lead to so many dangerous conditions and death, right? So that was the first thing. Second is your anoxia, the problem of anoxia. So what is anoxia? So in high altitude, what happens? At high altitude, pressure decreases, solubility decreases. That is why at high altitude in mountains, what you must have heard about is deaths, a lot of deaths. Why? Because some person is not able to, survive in that low pressure area, right? So our body, when it is not used to it, the body is used to surviving in this kind of climate where you have a proper pressure, atmospheric pressure. Your body can dissolve a certain amount of oxygen that your body requires. At high altitude, because pressure is low, solubility of oxygen is low in a hemoglobin. That is why it can lead to suffocation, and even to some person it can lead to death also, right? And one more application here, based on your temperature, that Here you can see, you can write here, two things you can write. Aquatic life, you can write aquatic life survive in low temperature. Can you tell me the answer of this? Aquatic life, right? Just like cold drink, right? We need cold drink, we want cold drink at low temperature because gas is more soluble. Same, the oxygen is in the ocean. How the aquatic life will get oxygen? From the ocean water, right? If oxygen is more soluble in the oxygen water, aquatic life can survive, right? So if the oxygen is less in the ocean water, the aquatic life cannot survive, right? So that is the reason sometimes you will see fishes on the border of the ocean. The reason is sometimes if they feel that in the ocean they have high temperature is very high for ocean, so oxygen solubility is less in the ocean. That is why you can see these aquatic life on the border area, right? Okay, over the oceans you will see these aquatic life. Because they also want to survive, they want to gain that oxygen. That is only possible when the temperature is low, right? Okay, next is, I think this also we have done. Now let us talk about the concept of vapor pressure. So I'll tell you a simple concept of vapor pressure. Very simply we'll talk about the concept of vapor pressure. So let us talk about this thing. You have a beaker, right? You have another beaker, right? You're adding these two beaker. Now you have another beaker. Okay. So I'm going to draw it. For example, this is my, I'm assuming it to be, this is my A compound, right? And this is my vapor pressure, right? When I'll heat this compound, or maybe in the atmospheric heat only, right, it will form some vapors right here that I am representing by green color. Next, I am representing one more thing, that is your B solution. It will also form some vapors here. It will also form some vapors. Next, I am representing when I have mixed these two solutions here, right? When I have mixed these two solutions here, right? So if I have mixed these two solutions, then I will have vapors of both A and B, right? I'll have vapors of both A and B, right? I'll have vapors of both A and B. Now, what is basically this vapor pressure, right? Vapor pressure is the pressure exerted by these vapors on this liquid. That is called vapor pressure. Simple. Pressure of that vapor is called vapor pressure, right? So the pressure that is exerted by these liquids, these vapors on the liquid, that is called the vapor pressure, right? That is called the vapor pressure. Now I am going to define two terms here, right? Very simple. I am going to define two terms here. One is your P naught, other is your simple P. That means one is your vapor pressure, other is your partial vapor pressure. So what does that mean? You should know the difference, only then you will be able to understand colligative properties. Otherwise, right? Yes, both should be volatile. Very good, my crab. Both, the condition is both should be volatile liquids. Volatile liquids means those liquids that can form vapors, right? Only those liquids, right? That will be there. Now, here I am presenting, this is your PA. So I'll mention that vapor pressure of a pure liquid, right? For example, here you have a pure liquid and it is forming the vapors, and the pressure that it is exerting on it is called P naught A. Why P naught A? Because this is a vapor pressure on a pure liquid, right? There is no competition here. Here you can assume that when you're sitting alone in your room, right? So that is your when you're sitting alone. Here when B is sitting alone, right? B is sitting alone, there is no interference of A, and here there is no interference of B. Here B is a liquid, it has formed the vapor because it is volatile, it will exert some pressure here, right? Third is when I am saying that you have a mixture of A and B. So in this case, when you and your friend are sitting together, tell me one thing. You will chit chat a bit, you will talk to each other a bit, right? So what will happen? your pressure will decrease, right? The amount of study that you can do alone, that will decrease. Now you're talking to each other. So basically, what is partial pressure? Partial means parts, right? Partial pressure is PA and PB, and partial pressure means that the pressure exerted by that component, the vapors of that component, when it is present in a mixture, right? Because here it is present in a mixture. If it is in the pure state, we will denote it by naught. If it is not in the pure state, we will denote it naught by naught, right? So it is simple, and the total pressure of this A and B will be PT, that we will define by total pressure, right? That we will define in some books it is written as PS as the total pressure. That is totally your choice. You can write anything there, right? So that becomes your total pressure. Right, so I'll write it here. These are the partial pressure, partial, and this is your vapor pressure. This is your vapor pressure of pure solvent, right? Of pure liquid, right? This is the vapor pressure of pure liquid, right? I think if you're able to understand the difference between pure vapor pressure, like vapor pressure, and partial vapor pressure, things will get very, very simple for you. How many of you understood the concept of vapor pressure and pure vapor pressure, right? Sorry, vapor pressure and partial vapor pressure. Now let us see on what factors it depends. On the nature of liquid. How much is the volatility of that liquid? How much vapors that is forming? That will define the vapor pressure. So for example, they are saying intermolecular forces is very strong. A is very strongly bonded to B. So A will be like, I don't want to break this bond. No, not AB. Let us talk about AA. So you have this AA. It is very strongly bonded to each other. So it is very difficult to break this bond. When it becomes very difficult to break this bond, that means its vapor pressure will be low, right? So more is your forces. It will be difficult to break your bond. It will be difficult to form vapors, and less will be your vapor pressure. That is why vapor pressure is inversely proportional to your intramolecular forces. Next is about temperature, right? So you don't need to understand this equation. That is the same equation that we have done in chemical equilibrium. The same thing we have done, right? So this is Claus-Caprion equation. You don't, because that is not in your syllabus. You don't need to get into detail of this, right? So at higher temperatures, just remember, at higher temperature, more molecules, because as the temperature increases, right, more molecules will get into vapors and more will be the vapor pressure. So just have to remember, as the temperature increases, vapor pressure increases. That's it. Okay, that's it. Right, students? That's it. For JEE Advanced, you can remember this equation, but otherwise don't remember. Right. Next is your vapor pressure, very important, does not depend on the amount of liquid, on the surface area of liquid, on the volume and shape of the container. What we have told you, it depends on the intramolecular forces, it depends on the temperature, right? Okay. Next is Raoult's law. Now, what is this Raoult's law? Here we will talk about the relation of partial pressure and your vapor pressure, right? So I will be taking up this diagram only, right? Because I am very lazy to draw it again and again, right? So now let us talk about this diagram only. Okay. So from here I will define the Raoult's law, right? So what Raoult told, Raoult said that this is your PA and this is your PB, right? That is your partial pressure. He said that the partial pressure of a component is equal to, is directly proportional to the mole fraction, right? It is directly proportional to the mole fraction of that component in the liquid phase. Why I am saying liquid phase again and again? Because there is a concept of mole fraction in vapor phase also, right? That is why I am mentioning again and again, because in the exam they will confuse you with liquid and vapor phase. So here it is in the liquid phase, not in the vapor phase. So partial pressure is directly proportional to the mole fraction in the liquid phase. So that means with the when we cancel the proportionality sign, we have P not A, and this is your mole fraction of A, right? Okay. What is the next thing? What is the next thing? You have PB. that is equals to P naught B, and this is your mole fraction of B. Same with the component B, when it was alone and now when it is in the mixture, right? Okay. Now, from this equation, this is 1 and 2, we also know what is the total pressure here. Total pressure will be PA plus PB, and that is going to be, total pressure is going to be, what is PA? That is P naught A, mole fraction of A, plus P naught B, mole fraction of B. This is basically your Raoult's law. This is what we say when we talk about Raoult's law, right? Okay. So now let us see the definition here. The partial pressure of any volatile constituent of a solution at a constant pressure is equal to the vapor pressure of pure constituent. Pure constituent is this one. Pure constituent is this one, multiplied by pure constant multiplied by mole fraction of that constant in the solution in liquid phase. You can write in liquid phase. Mole fraction in the liquid phase. Okay, so that becomes your answer. Now, I will further elaborate this equation, right? So, what is your equation? That PT. What is your equation, everybody? It's not like they will ask you directly this equation. You have to make the other forms of this equation as well, right? So, let us derive this. Very good, Sukanya, Shabash, very good. So, let us derive this. This is your PT is equals to P naught A, mole fraction of A, chi A, we will remember. P naught B of chi of B, right? So, what is your PT? I told you one thing, that chi of A plus chi of B, because it has two components, right? So, the mole fraction of all the components is equals to unity. So, for example, you want to write it in the form of mole fraction of A, right? So, you would say mole fraction of B is equals to 1 minus chi A. So, just put it here, P naught A chi A plus P naught B 1 minus chi A, right? So, it will become P naught A chi A plus P naught B minus chi A minus P naught B chi A. Just take out chi A common from this and this. So, chi A we have taken this common, right? We have taken this common, and this is P naught A minus P naught B plus this is your P naught B. This will stay as it is. Now, we have taken from this and this, we have taken common from this and this, right? So, chi A common, P naught A minus P naught B plus P naught B. So, can I write it this as PT equals to P naught B plus chi A P naught A minus P naught B, right? I will give you a simple trick to remember this, okay? So, now I have written this in the form of chi A. If I want to write this in the form of chi B, what I will do? In the form of chi B, I will say PT equals to P naught plus chi P naught minus P naught. Ma'am, what you have not mentioned AB? I'll tell you. Here you have B, A, B. Here you will write A, B, B, A, right? So, this will become your next. So, what you have to do? P naught plus chi, P naught minus P naught, B, A, B, A, B, B, A, right? Abba, Abba, Baba, Bab, Abba. Okay? Understood? Yes, students? Everybody in the chat box? These are the two equations of Raoult's law. Very, very important equations, right? You can even learn it with this concept, right? You can even learn it with that concept. That's totally your choice, right? Okay. I think that we have done. Now, let us see the graph of Raoult's law. So, this is basically the graph of Raoult's law that you must have seen so many times. So, basically at this point, you have chi A equals to 0 and chi B is equals to 1. At this point, your chi A is 1, that your mole fraction of A is 1, but your mole fraction of B is going to be 0, right? So, from this line to this line, basically, if I am talking about this line to this line, right, this line is representing PA, right, P naught A, right? And this line, when you are taking this line from the B point to this point will represent the P naught B. And when you join P naught A and P naught B, you will get the total pressure, right? That I represent by PT, but they are representing by PS, so you can define anything here. So this is PT equals to PA plus PB, right? So here it is P naught B and this is your P naught A. This is a graph of ideal solution that will follow Raoult's law. Now tell me, are you an ideal student or not? So basically, just like we had ideal gases, right, that follows ideal gas equation are the ideal gases, which do not follow ideal gas are the non-ideal gases, right? That is not in your syllabus abhi, but that used to be in your syllabus in states of matter, but now you don't have that. So basically, an ideal person is that one who is, an ideal person is that who is able to do everything. For example, I have told you that complete all the NCERT questions today, complete all the DPPs today, complete this and that, everything you should do today. So ideal person is that who is actually able to complete everything. But a non-ideal person like us, they will try to complete, but may or may not be. Some days they will be able to complete, some days they will not be able to complete. So basically, ideal situation is that which follows everything, right? And there are like hypothetically there are ideal solutions, right? Yes, there are ideal solutions, but very less, right? So follows ideal's law, follows Raoult's law is the ideal solution. Which do not follows Raoult's law is the non-ideal solution. Let us talk about ideal and non-ideal solution. Achha, before that, there is one concept of special case. Raoult's law as a special case of Henry's law. Very simple. So let us talk about Raoult's law as a special case of Henry's law. What is Raoult's law? Raoult's law is partial pressure of A is equals to P naught of A into chi, right? And what is Henry's law? That is your partial pressure, for example, I am talking about A component only, is equals to K of KH, that is your Henry's constant, into mole fraction of A. So what is the different thing? Can I say rest of the things are same? This is P naught A and KH. If P naught A becomes KH, then Henry's law and Raoult's law are the same thing only. Right, so that is why we are saying the comparison of equation, what we can say that partial pressure is directly proportional. Only difference in the expression is that is your P naught A and your KH. So Raoult's law becomes special case of Henry's law in which KH becomes equal to P naught. When KH will become equal to P naught, that will be a special case of Henry's law. Right, Raoult's law basically when your KH is equals to P naught, that becomes a special case of Henry's law, right? Okay, yes. Now, let us talk about ideal and non-ideal, right? After that, I'll give you break and after that, we will do colligative properties, right? Okay? Okay? Yes? Okay. So now, if I talk about ideal and non-ideal solution. In ideal solution, the one which follows Raoult's law, everything is doing perfect, right? Yes, I'm a good dancer. You know those kids who are like, I'm a good dancer, I'm a good singer, I'm a good actor, I top in the class, I'm also very good in partying, I'm also good in everything, I'm also an extrovert, I'm good in everything, also in stage. You know, these kind of people, right? I was not that kind of person. But some students are extraordinary, right? Extraordinary. Very rare students who are like that, right? So we are good in everything, like everything, right? So this is that ideal solution that is good in everything. So solution which follows Raoult's law over the entire range of concentration, anything happens, they will follow the Raoult's law. AB interaction. So basically what happens here? What is the reason for that? Why, ma'am, they are behaving as ideal? Okay, tell me one thing. Tell me one thing. There is a kid to whom it doesn't matter that his best friend is sitting, his or her best friend is sitting next to them. Their stranger is sitting next to them. Their sibling is sitting next to them. It doesn't matter to them. For example, they are sitting alone and studying, they will behave the same. For example, some stranger come in their life, they will behave the same. For example, their best friend come in their life, they will behave the same. Right? That is the ideal situation. Anything happens, they will behave the same. That means the interaction when A is sitting alone, when B is sitting alone, and when A, B are together is same. Right? These interactions are same. It doesn't matter to them whether they are sitting alone, whether they are sitting with someone. Right? They are completely like totally ideal situation they are in. AB interactions in solutions are same as original AA and BB. It doesn't matter who is sitting next to them. Right? Do you know any of such person? Or are you that person? I am definitely not that person. So, this is delta, as you can see in our live sessions only. When I am with Shreya sir, when I am with Baswa sir, and when I am with Gopika ma'am, I have a different kind of, case. I am a different person then. Right? Why? Because when I'm sitting next to the people, right, whom I can interact with, I'll behave differently, right? So I am a non-ideal solution, right? If you know any of the ideal solution, write it in the comment section, right? So here you have ideal solution. In ideal solution, nothing will happen. No energy released, no energy absorbed, nothing will happen. Delta H is 0. Volume, delta V 0. What does that mean? That means if you're adding 10 ml of A solution, you're adding 10 ml of B solution, your answer will be 20 ml only. It will not be 19 ml. It will not be 22 ml. There will be no interactions there. There will be no association, no dissociation, because of which volume will vary. Right? So volume will be same as V1 plus V2. Right? Next is non-ideal solutions. Non-ideal solution are who are like, okay, a little amount of distraction. They will study. Best friend is coming, oh, hi, how are you? Arey, you know about that person, you know about this thing, this chapter is so difficult, oh my god, this, that. They will talk about all the things in this universe, right? So they are our non-ideal situation. Not only with best friends. For example, some stranger is sitting next to them. They will also think about something that, okay, right? Someone is there, right? Someone is there, right? So basically, any person out there will come in their life when they are sitting alone, studying in the library. Any person will think, they will make up some story about them, right? Okay, so these are the non-ideal situations. I used to do this when I used to study in library, So I used to go because I was like, okay, I don't want any person that I know, like around me when I am studying. So I used to go in the library. At one point, I used to see similar faces like in the library. Then I used to pass smile. I was like, yes, or good, yes. So I was like, why I am making friends in library? I was supposed to be here because I don't want any friends. I don't want my friends to be there when I am studying. Now I am making friends in library. So I was like, okay, I am that non-ideal solution, which is like too much interactions is going on, right? So here you have solutions which do not obey Raoult's law, right? They will not behave ideally, right? And forces of attractions, right? For example, there can be two cases. Either AB can have more or less force. That means they are not equals to AA and BB. For example, when you're sitting alone, you are behaving differently. When you're sitting next to that stranger or next to that best friend, then you are behaving very differently. So the interactions are not same. Your focus on your study is not same, right? So that is the reason your delta H mixing is not equals to 0. Your delta V mixing is not equals to 0, right? Here, because it is not following Raoult's law, so you can say that P A is not equals to P naught A and chi A. PB is not equals to P naught B and chi B, and P total is not equals to P naught A chi A plus P naught B chi B, right? So basically these are the things that it follows. Now let us see more about these more about these non-ideal solutions. So non-ideal solutions, they are of two types. One is your positive, second is your negative deviations. I'll just give you, because from here the questions are asked, from examples as well the questions are asked, from definition as well the questions are asked in your exam. right? So see this very, very carefully. Students usually get confused in this, right? So let us see this. Here you have positive and negative deviation. How to remember this thing? For example, you and your best friend. Your best friend arrives. You're like chit-chatting with them, gossiping with them, this and that, right? So what will happen? Your concentration in your studies will decrease or increase. Everybody in the chat box, if your best friend arrives, right, in your room, right? So in your room, what will happen? You were studying alone. You're like fully focused. Now your best friend is present. Now you're like, okay, let's eat something. After that, we will study. Okay, let's talk about this topic. After that, we will study. We'll study after 10 minutes. What will happen? Your concentration will decrease. Concentration means not that concentration, means your focus on your studies will decrease. Negative thing will happen here. I wanted you to complete 100 questions, but because of your best friend, because of the gossiping thing, you are not able to focus. You want to enjoy, you want to have fun, right? So your negative deviation is there. That means here, because your interaction of AB is greater than AA and BB. When you guys were sitting alone, your interactions were good. You were like, okay, you were studying. But now when you're together, you have like more interactions with each other. That is why your focus on studies is less. That is why it is a negative deviation. And that is the reason your pressure will decrease, right? That is the reason the pressure will decrease. That is the reason we say pressure total is less than as compared to P0A 𝐸A plus P0B 𝐸B, or you can also say PA is less than P0A 𝐸A, PB is less than P0B 𝐸B, right? What about this? In positive deviation, for example, some stranger is sitting next to you, right? Inversely proportional to concentration. That's true, right? For example, some stranger is sitting next to you. Now you don't care about that, right? You're like, okay, this stranger is sitting next to me. Okay, let me focus. Oh my God, this person is studying a lot. Oh my God, I don't know this person. You will be like, okay, I will study a lot. For example, your competitor is sitting next to you. You don't know that person, right? But you know this person is a topper. So you will get, the interaction will be there, right? But that will be a thing which will motivate you to study more, right? So that is your positive deviation, right? You are deviating. You are not in a normal state, but you are studying more. You're like, oh my God, I have to study more. I have to beat this person, right? So partial pressure of each component A and B are higher than the calculated from the Raoult's law, right? So basically here you can say your interaction of AB is less than AA and BB interactions, right? This question has been asked to you so many times. They will ask you about interactions definitely, right? Then your pressure, so you can easily say that your total pressure is greater. That means PA is greater than P0A 𝐸A and PB is greater than P0B 𝐸B, right? P0B is greater than PB 𝐸B. Is it? Yes, students? Now, next is the graph. Firstly, you draw the graph of ideal solution. Then, we know that the pressure is being increased here. The pressure has increased. So, it will be more. PA has also increased. PB has also increased. So, pressure will be more. When the pressure is less, PT has decreased because PB has decreased because PA has decreased. That is your negative deviation, right? So, simply what you have to do, you have to increase the pressure in positive, you have to decrease the pressure in negative deviation, right? Okay, simple graph. Just draw the graph of ideal gas. Then here you increase the pressure, it will be more, right? Here you decrease the pressure, it will be less. The curve will be outward, here the curve will be inwards, right, students? Yes, now very, very important page. So very, very important page. Take a screenshot of this. Take a screenshot of this because, these questions, I'll tell you how to remember these things, right? Okay, I'll tell you how to remember these things. Now, if you talk about when the interactions are decreasing. Firstly, let's talk about when the interactions are increasing. Water with any acid water with any acid, whether it's HCl, whether it's HNO3, whether it's acetic acid, any acid, water with any acid, basically what will happen? No? In water, you have an acid, right, that has a covalent bond. So when you dissolve water in it, it will split into ions, right? In the aqueous solution, it will split into ions. Now, ionic bond is stronger as compared to covalent bond. That is the reason when you add water in any acid, in that case, what will happen? Your ionic bond strength will increase. That is the reason your interactions will increase. That is why it is a negative deviation, right? So, water, write it. Will be uploaded, ma'am. Notes will be uploaded on the Telegram channel of Vedantu NEET English official, right? Okay. Okay. Now, water with any acid. Next is your chloroform and methyl acetate, right? Because of this chloroform, what is chloroform? That is CHCl3. Because it is a non-polar thing, right? So, what it will make? It will start to make more interaction with this methyl acetate, right? That is the reason here the interactions will increase. Acetic acid and pyridine, one is acid, other is base. Now pyridine, basically we know that in pyridine you have this N which has lone pair of electron, and in acetic acid you have CH3COOH, right? This is negative, this is positive. So this will try to attack on this, right? There will be H positive. That is why they will have strong interaction. One is acid, one is base, right? Then you have phenol and aniline. Again, this is your basic in nature, this is acidic in nature. Because of that, they will have more, you can say they will have more interactions, right? Okay, then what about this one? Chloroform and water. Here in this case, the interactions are going to decrease. It's a non-polar thing. Here the water had strong hydrogen bonds, but when you will add chloroform, that is your CHCl3, the hydrogen bonds will break, right? That is why the interactions will decrease. Here you had non, you had H bond, again you had H bond. Now, when you add CCl4, the hydrogen bond of this ethanol will decrease. That is why the interactions will decrease. Here you have methanol and chloroform, same concept. Then you have benzene and methanol. Again, this had hydrogen bond, right? But with the addition of a non-polar solvent, the hydrogen bond will decrease. Again, you have acetic acid. Acetic acid is existing as a dimer because of the hydrogen bonding here. But when you add toluene, the interactions will decrease. Acetone and ethanol, right? Ethanol again has hydrogen bond, right? But when you will add acetone, the interactions will decrease because hydrogen bond will break. Now, between methanol and water, both have hydrogen bonds, but your water has more hydrogen bonding. Why? Because water has OH and H, but methanol has OH and R. Because of this larger alkyl group here, the strength of hydrogen bond will be less as compared to water. That is why on adding methanol to water, the strength of the hydrogen bonding will decrease, right? What about this C2H5 and cyclohexane? Again, this will have hydrogen bond. When you add cyclohexane, the hydrogen bond will decrease, the strength of interaction will decrease. That will be a positive deviation, right? Okay. So, I told you the reason behind all of these examples, right? The chloroform examples are really, really important, right? Okay. Otherwise, all the examples are important, right? Okay. Now, let us talk about azeotropic mixture, which is similar to this, which is very similar to this. Okay. Okay, students, let us talk about azeotropic mixtures, everybody. Let me see how many of you have liked the session. How many of you actually shared the session? Huh? So much hard work I do for you. How many of you actually share the session among your friends, right? So spread the word, right? And if you really like my teaching, then share this among your friends, right? Okay. So that would be a great thing, right? Because we are also doing a lot of hard work for you, right? Okay. So now, when we talk about azeotropic mixture, right? Firstly, understand the boiling point, right? For that, firstly, you have to understand what is a boiling point. Tell me, students, what is a boiling point? A boiling point, this is your cutoff of NEET. You are here, right? You want to reach this position only, then you will get to your favorite medical college, right? Similarly, for any liquid, the cutoff is the atmospheric pressure. So when your vapor pressure of that liquid is equals to atmospheric pressure, that means you have reached your boiling point, right? So you were at this position, you are burning yourself, you are heating yourself. Why? You are studying daily, consistently you are studying, right? Here, sitting there for hours and hours. Now you're converting into vapors. At one point you will reach your cutoff. You will get into that medical college. Same with this liquid. This was at this vapor pressure, this is the atmospheric pressure. So when we're increasing the temperature, the vapor pressure increases. At one point it has reached to the atmospheric pressure. This is when we say it has reached its boiling point. This is when we say, yes, it has reached its boiling point. So what is the boiling point? That you have to understand, right? So I hope so that is clear. What do you mean by it? Not only definition, you have to understand what is this atmospheric pressure, what we have to do. Because with this relation only you will be able to understand. Right now I am preparing you for colligative properties, right? This is also individual concept, but this is also applied in colligative properties, right? So basically, if you talk about an easy way, I'll tell you. So tell me one thing, if I talked about this positive deviation, right? In this positive deviation, earlier my pressure was this for an ideal situation. This is my atmospheric pressure, right? This is my atmospheric pressure. This is my pressure of that liquid in ideal situation, right? Now, if it is a positive deviation, the pressure will increase. Earlier it was here, right? This is the atmospheric pressure, earlier it was here, right? The pressure will increase because here we have seen the pressure has increased. The pressure will increase because of positive deviation. Earlier it was here, it had to jump this much thing. Boiling point was really high. It has to increase this much thing. It has to jump this much. But here the pressure has increased. Now the jump is less. That means the boiling point has decreased, isn't it? In positive deviation, can we say the boiling point has increased? Right? So what I'll write here, positive deviation means minimum boiling point. Because boiling point has decreased here, right? Now, next concept is, for example, this is your atmospheric pressure. Now, this was the pressure of the liquid in the pure state. Now, the pressure is negative. There is negative deviation. The pressure here, it will have to jump like this. This was the jump, right? This was the jump. But now the pressure has decreased. Now the jump is larger, right? That means here we will use maximum. For negative deviation, you have maximum boiling point. Why I am telling you this? So that you are able to understand the azeotropic mixture. Okay? So can I write here, for positive you have minimum boiling point. For negative you have maximum boiling point. Why I have told you this? Because 2-3 questions they can ask you from azeotropic mixture. One question what they can ask you, what is exactly, ma'am, an azeotropic mixture? You have not told us that. So what is an azeotropic mixture? It is a binary where you have one solute solvent, basically you have two kind of solutions. It's a binary mixture having same composition in liquid and vapor phase, right? What do you mean by that? In liquid phase, your mole fraction is chi, and in vapor phase, for example, I'm talking about a component A. In vapor phase, your mole fraction is Y. This is what I was telling you. That in liquid phase, the mole fraction is regarded as chi. But in the vapor phase, like in this, for example, I am talking about the mole fraction of, this liquid. That is represented by chi A. But for this vapor, that is represented by YA. Right? Here it is represented by YB. Here it is represented by chi B. Right? So that is in the liquid state. This is in the vapor state. The mole fraction in the Now, vapor state, okay? You can see 3 to 4 questions from here, right? So, yes. Now, let us see. Binary mixture having same composition in the liquid and the vapor phase and boil at, second thing is, first thing is, you should know the properties here. Liquid and vapor phase, the mole fraction is same, right? Same composition they have. Second important thing is they boil at constant temperature. Now tell me, what was distillation? What was distillation? I told you in the purification concept, what is distillation? Distillation is very simple. Distillation means you have to separate two mixtures, right? How to? By the difference in the boiling point, right? There should be main criteria is the boiling point, right? We have seen very high change, very high difference in the boiling point, very less difference in the boiling point, everything we have seen. Here they are saying the boiling point is exactly same. Tell me, if two mixtures have same boiling point, will you be able to separate them? How can you separate two mixtures which have exactly the same boiling point? Not even 0.1% difference is there, right? So, it cannot be separated by fractional distillation. You cannot separate this by distillation, right? Okay, this is the first question they can ask you regarding the properties of the azeotropes. They have same composition in vapor and liquid phase. Second is they are not separated by distillation because they have same boiling point. Another question they can ask you about the examples. So if they ask you the minimum boiling azeotrope, you will give the examples of positive deviation. If they ask you maximum boiling azeotrope, you will give the example of negative deviation. All the examples that we have done here, right? So positive deviation is minimum boiling azeotrope, minimum boiling, and this is your maximum boiling, right? So they can, earlier they used to ask with what is the, which of the following is an example of positive deviation, negative deviation. High chances are that they can ask you this in the form of azeotrope. Which of the following is an example of minimum boiling azeotrope, maximum boiling azeotrope? You just have to, same thing will be applied here, right? Okay. Very good, Sakshi. Very good, very good. Practice session on this chapter. Yes, you must do that. You must do that because without practice, so nothing will happen, right? So here you have some, in detail, we have written the examples. Mixture of two liquids whose boiling point is less than either of the pure components. Boiling point has decreased. That means positive deviation they are talking about. Found by non-ideal solution showing positive deviation. They are found by showing negative deviation. Right, these are the examples. Here in percentage they have given you, but you don't need to remember this in percentage. Just remember the examples of positive deviation, remember the examples of negative deviation. That's it, you are sorted for that, right? Okay. Now, next is your exercise question, right? So let us see these questions, right? After that, I think we'll start with the colligative property. Yes, one more thing. Yeah, one more thing you need to write down here. Where should I write it? Where should I write it? I'm writing it here itself, right? Wait a minute. I'm writing it here itself. YA mole fraction, because this can also be used. Mole fraction in liquid phase. No, it's in vapor phase. If they ask you the mole fraction in vapor phase, then what will be the formula? So, your your P of A, partial pressure of A is equals to Y of A into partial pressure total. And if you talk about the mole fraction in in liquid phase, that will be PA is equals to P naught A chi A. Right? So these are the two very important things, right? Write it down. They can ask you this, right? Very, very important. Okay? Yes, students? Yes, students. Yes, students. Sure. Now, I think let us do the questions now. 2-3 questions we are left with. Then we will start with the colligative properties after the break. Okay, I'm just going to tell you the overall scenario of this question. I'm not going to solve like the one in one step because we have to complete this chapter today, right? Because calculation you can do that yourself, right? Whatever help is needed, that I'll give you. Heptane and octane form ideal solution. They are saying heptane and octane, they are forming ideal solution. The vapor pressure of two liquids. How to do the numericals? Just see how I'm doing the numericals, right? So, the vapor pressure of two liquids components are this and this. What will be the vapor pressure of mixture? That means P naught A is given to you. Instead of A, what I'll write? I'll write for heptane it is H, for octane it is O. So I'll write P naught H is given to you, that is your 105.2 kilopascal. What is H, P naught of octane? That is your 46.8 kilopascal. So that's why I was telling you about this thing, that you should know how to identify which is P naught and which is P. Now they have asked you the vapor pressure of a mixture of this much of heptane and this much of octane. Now weight of heptane is given to be 26 gram, right? And weight of octane is given to be 35 gram. We know what is the molar mass of heptane, you can calculate, right? Molar mass of octane, you can calculate. You have the molecular formula. You can calculate the molar mass of both of them, right? So after this, can you calculate the number of moles of heptane? You can calculate the number of moles of octane. From there, chi of heptane also you can calculate, chi of octane also you can calculate. What is chi of heptane? This is basically your number of, this is W of H by M of H. This is your W of O by M of O. And this is your N of H divided by N of O plus N of H. This is your N of O divided by N of H plus N of O. So we have calculated the chi also here. Just apply this formula. P H is equals to P naught H multiplied by chi H. Chi H you have calculated. PO is equals to P naught O into chi O. Right? Okay. Easy. I have told you everything that we can do here. Right? Yes. Your answer will be in kilopascals only. Right? So this is the same thing that they have done. Right? Vapor pressure is given. Molar mass, that is 100. And for a number of moles they have calculated. Then molar mass of octane. Then you have number of moles you can calculate. Then you have to calculate mole fraction of both of them. Mole fraction you have calculated. Then you will calculate the partial pressure of both of them. Right? Then total pressure will be the partial pressure of pH plus PO. That is going to be your total pressure. Tell me, beta, is that clear to everyone? Is that clear? Simple, direct question it is. Right? Direct question it is. Right? Next is in the water saturated air. It's a very, very important question. Very, very, very important question. Right? Because of this question only I told you that they can ask you about vapor pressure mole fraction also. So from this you will be able to understand what exactly I was telling. Right? So in water saturated air, water has dry air as well. It has water vapors. That means your wet air as well. Mole fraction of water vapor is this. Mole fraction of water vapor. Now water vapor, that means in the vapor phase they are talking about. So talking about Y of water vapor is equals to 0.02, right? The total pressure of the saturated PT is equals to 1.2 atmospheric. The partial pressure of dry air. Okay, tell me one thing. I told you about one formula, that your partial pressure of your dry gas or your water vapor or any vapor state will be equals to the mole fraction in the vapor state multiplied by total pressure. So can I say that will be 0.02 multiplied by 1.2. That will be 0.024. Isn't it? Can I say that? I have written this formula, right? So your pressure, partial pressure of that vapor phase is equals to mole fraction in the vapor phase multiplied by total pressure, right? Now this is about water vapor. That means this is for wet air. This is for wet air. This is not for dry air. So total air, that means total pressure of that air is equals to pressure of dry air. Dry air, you can write dry air plus pressure of water vapor, that is your wet air, right? Pressure of water vapor, you already know. Pressure of water vapor you have calculated. You need to calculate pressure of dry air. That will be P of T minus P of water vapor. So what is P of T? Total pressure is 1.2 minus it is 0.024. This will become your answer. I think this will come out to be 1.176. Right? Is it? Yes, it is coming out to be 1.176. Okay? 1.176. That will become your answer. Right? Okay? Arey, no issues, Neha. You don't need to delete your messages. Right? I will not scold you or I will not do anything with you. Ki, okay, are you not able to tell me the correct answer? You tried, that is enough. Right? Okay? You will do mistakes now, it's okay. Right? Just don't do it in exam. The mixture, now 2020 question. The mixture which shows positive deviation from Raoult's law. Any answer students? The mixture which shows positive deviation from Raoult's law. Ethanol, acetone, benzene, toluene. Positive deviation. Positive deviation means your interaction should be less. Interaction should be less. So, this to definitely not. Benzene, toluene is also ideal. Ethanol and acetone. Acetone and chloroform. Interaction should be less. So, A will be the correct answer because this already has a hydrogen bond. On adding acetone, its hydrogen bond will decrease. Right? So, here option A is the correct answer. Next is, now as I told you, they can also ask you in the form of 2019 question in the form of azeotropic mixture. Right? So, the mixture that forms maximum boiling azeotrope. What do you mean by maximum boiling azeotrope? That means they are showing, maximum means they are showing negative deviation, right? Maximum means they are showing negative deviation. So what is the form, if you talk about negative deviation, that means the interaction of AB should be strong, which are forming good interactions. This definitely no. Water and nitric acid, definitely it is forming. I told you water and any acid, right? It will form ionic bond, right? Water and any acid, it will form ionic bond. With ionic bond, the interaction will increase. So, answer will be B for Baswa sir is the correct answer. Okay? Yes, very good. Now, I think next is about colligative properties. So, let us take break for 5 minutes and after that we will start doing the colligative properties, right? Okay? So, before that, as you guys are talking about practice, as I'm telling you that I can I can teach you that how to do this concept, but in the end, you have to practice yourself. Now, this is the best time to do the practice. So, that is why we have this offer for you, where we have NCERT based test series for you, right? From here, we all know that in NEET, NCERT based questions are asked, right? So, your NCERT based questions, based test series for your NEET exam we have. And right here what you will get 25 total tests, you will get detailed video solution, real exam like, and you have 360-degree performance report will be given to you. Moreover, with this we are giving you DNA batch for totally free of cost, that is complete NEET 2025 preparation, that everything will be given to you, full syllabus coverage, exclusive membership and guidance, daily practice and rewards, right? So, who are in the DNA batch, they already know, right? So, this is available at just 2499, right? At just 2499, and this is a very limited time offer, right? So, if you want to get enrolled to this, right, you will have DNA batch, you will have year-long test series, right? And that is also NCERT based, especially for NEET, right? So, the link is in the description. You can go and purchase this. That's a very less amount. We are giving you two things here, right? So, the link is in the description, right? and you think, you talk to your parents, right? Talk to your friends about this, right? And then take a wise decision, right? Because you just still you have time for practice, right? Okay, that's why I'm telling you. Now we have break time and I'll be here at 12:20, right? At 12:20 p.m. I'll see you all. Okay? Yes. Launch break. No, you will not have launch break, right? So you can have your lunch, right? So I'll see you at 12:20 p.m.